Now we embark on the precise line of thinking that completely dominates my investing and purchasing habits, and I call it energy economics. When oil first began to be used for industrial purposes, world population stood at 1.5 billion and sailing ships still plied the waters alongside coal steamers. Since then, population has expanded more than 4 times, the world's economy by more than 20 times, and energy use more than 40-fold. We are all familiar with the massive benefits that accrued from this explosive liberation of human potential. In order to appreciate the delicacy of the continuation of this abundance, we need to understand the actual role of energy in forming our society. If we recall back to Crash Course Chapter 5, I made the point that both growth and prosperity are dependent on surplus. They are, and so is one other equally important social element. If we make this yellow box represent the total food energy available to a people, and then set it to exactly equal the amount of food those people need to get more food to stay alive, then we'd find that their society would be very rudimentary and not terribly complex. If instead these same people were able to produce just 1.2 calories for every 1 calorie expended, then they'd have the exact energy balance that existed in medieval times. This skinny 20% surplus allotment of energy is sufficient to allow rich hierarchies to form, job specializations to develop, and large works of architecture to be built. With sufficient surplus energy, humans can construct remarkably complex creations in short order, as these pictures of oil-rich Dubai taken only 17 years apart attest. Now we can state the 13th key concept of the crash course. Social complexity relies on surplus energy. Societies that unwillingly lose complexity are notoriously unpleasant places to live. Given this, shouldn't we pay close attention to how much surplus energy we've got and where it comes from? This is why we're going to take a quick tour through the concept of energy budgeting. It's the same as household budgeting, but we leave dollars out of the equation. It works like this. At any given time, there is a defined amount of energy that is available to use as we wish. Let's put everything into this yellow square. Solar, wind, hydro, nuclear, coal, petroleum, natural gas, and anything I've happened to miss. That's our total energy budget, and we can use it any way we wish. But if we want to have more energy next year, we obviously are going to have to invest some of that back into finding more energy. And then we'll also have to invest some in building and maintaining the capital structure that allows us to collect and distribute that energy, and to maintain a complex society. Roads, pipelines, bridges, electrical pylons, and buildings all go into this category of capital. Now, what's left over can be used for consumption. Part of this goes to basic living needs, such as water, food, and shelter, leaving the rest for discretionary things like trips to the Galapagos and hula hoops or attending Burning Man. To simplify this even more, we can divide energy up into 2 big buckets. Energy that must be reinvested to keep everything going, and energy that we can more or less choose what to do with. This is exactly analogous to your earnings. Suppose that your household earns $50,000 a year, and your total taxes are 30%, or $15,000. This leaves you $35,000 to buy food, pay for your shelter, purchase gasoline for your car, and maybe do a few other things besides. If this suddenly flipped around, and you found yourself with only $15,000 of take-home pay, your situation would change drastically. Perhaps you could only afford food and shelter, while the car and electronics and maybe vacations became distant memories. Your life would be forcibly simplified in terms of the number of things that you could afford to buy or do. So I want you to begin to think of the amount of energy that we have to reinvest in order to get more energy, is the same thing as an unavoidable tax on your salary. And here's why. Forget all about how much money energy costs, because it's actually irrelevant, especially when money is printed out of thin air. Instead, we're going to focus on how much energy it takes to get energy, because as I'm going to show you, that is what really matters. Fortunately, the concept's easy, and it's called net energy. The way we're going to measure this is by dividing the amount of energy we get by the amount of energy we had to use in order to get that energy. Energy out over energy in. Energy in is the tax, while the energy out is your take-home pay. Imagine that if the total energy it took to get an oil well drilled was 1 barrel of oil and 100 barrels was found. We'd say that our net energy return was 100 to 1. In this example, the tax we paid out was 1 out of 100, or 1%. Another phrase for this that you may encounter is energy returned on energy invested, which goes by the acronym EROEI. We're just going to stick with energy out divided by energy in for this section, or net energy, as it's easier to visualize and it's essentially the same thing. Now, let's make this visual by graphically comparing the relationship between energy out and energy in. The red part is the amount of energy we have to put in, and the green part is how much we got out, or the net energy. And we're displaying them such that they always sum to 100%. In this first scenario, the energy out divided by energy in yields a value of 50, meaning that 1 unit of energy was used to find and produce 50 units of energy. In other words, 2% was used to find and produce energy, leaving us a net 98% to use however we see fit. We could also call this part the surplus energy available to society. Even at a net energy ratio of only 15, the surplus energy available to society remains quite high. This surplus energy, of course, is what supports all of our economic growth, our technological progress, and our wonderfully rich and complicated society. Now, I want to draw your attention to what happens over here on this part of the chart between the readings of 10 and 5. The net energy available to society begins to drop off in a manner that should be familiar to you after seeing the section on exponential charts. Only this hockey stick points down. Below a reading of 5, and the chart heads down in earnest, hitting 0 when it gets to a reading of 1. When it takes 1 unit of energy to get a unit of energy, there is 0 surplus, and there's really no point in going through the trouble of getting it. Below a reading of 5, we are on the energy cliff. To find out why this is an enormously important chart, let's look at our experience with net energy with respect to oil. In 1930, for every barrel of oil used to find oil, it is estimated that 100 were produced, giving us a reading of 100 to 1, which would be way off this chart to the left. By 1970, fields were a lot smaller and the oil often deeper or otherwise trickier to extract, and the net energy gain was now down to a value of 25 to 1. Still a very good return with lots of green beneath it. By the 1990s, this trend continued, with oil finds returning somewhere between 18 and 10 to 1. And today, it is estimated that recent oil finds are returning only 3 to 1 net energy. Why is this net yield dropping? Because in the past, a relatively small amount of energy was required to create the metal for a smallish rig, and the finds were massive and plentiful and relatively shallow. Today, much more energy is required to find energy. Exploration ships and rigs are massive. If we put our humble 1930s rig to scale, it looks like this. And today, more wells are being drilled to greater depths to find and produce smaller and smaller fields, all of which weigh upon our net energy return. And what about the allegedly massive amounts of oil contained within the so-called tar sands and oil shales, the ones that are often described as equivalent to several Saudi Arabias? The net energy values for these are especially poor and in no way comparable to the 100-to-1 returns found in Saudi Arabia. Further, the water and environmental costs associated with them are disturbingly high. And what about renewable energy sources? Methanol, which can be made from biomass, sports a net energy of about 3, while biodiesel offers a net energy return of somewhere around 2. Corn-based ethanol, if we're generous, might produce a net energy return of just slightly over 1, but could also be negative according to some sources. If we add in all the other new sources for usable liquid fuels that we just talked about, we see that they are all somewhere on the face of the cliff. Unless we very rapidly find ways of boosting the net energy of these options, we'll simply find far less surplus energy for our basic needs and discretionary wants. Solar and wind are both capable of producing pretty high net returns, but these are producing electricity, not liquid fuels, for which we already have an extensive investment in distribution and use. Oh, and by the way, where's the so-called hydrogen economy on this chart? Right here. Because there are no hydrogen reservoirs anywhere on Earth, every single bit of it has to be created from some other source of energy, at a loss. In other words, hydrogen is an energy sink. In creating hydrogen, we always lose energy, and that's not pessimism. That's the law. The second law of thermodynamics, to be exact. Because hydrogen is a carrier of energy, not a source, it is more accurately described like this: a battery. Now, to make an absurd argument, because nobody would be this foolish, suppose Congress made the decision to, say, try and run our society on corn-based ethanol. What could we expect there? Well, if we adjust our graph to reflect that decision, we'll see a whole lot of red and very little green. The tax is very high, while our take-home pay is very low. By way of commentary, I find it somewhat telling that out of all the possible alternative energy sources, this is the one that Congress chose to advance. I mean, short of directly launching barrels of oil into outer space, it's hard to imagine a much more foolish idea. The important point here, though, is that even if the government completely subsidized ethanol to the point that it only cost you a penny a gallon to buy, we would soon find ourselves ruined. And the reasons why have already been covered. With less surplus energy, less societal complexity is possible. Under an ethanol regime, we'd find that many cherished job positions would simply vanish. Regulatory compliance specialists for food additives would have to revert to being farmers. Pediatric radiological oncologists would become healers, and Midwest regional communications coordinators for Special Olympics would have to find something else to do, and so on. If we tried to live on ethanol as a liquid fuel, we'd quickly lose nearly all of the specialized jobs that we associate with modern society, because there would be practically no surplus energy to use in support of that complexity. This diagram, with a rich balance of reinvested and consumed energy, would rapidly become this. Because of their low net energy, ethanol and other such poor energy sources are thoroughly incompatible with our current lifestyles. This turns into this. So let's review the two key concepts so far before moving on. Number 13, the price of energy is irrelevant. Net energy is everything. On this basis, both corn-based ethanol and hydrogen are dismal failures. Key concept number 14, social complexity is built upon surplus energy. If we want to maintain our society in its current form, we're going to have to master this concept and fast. Now, on to Chapter 17C, Energy and the Economy. Thank you for listening.